I'd like to talk about one of the most common types of cells used in liquid crystal displays today. It's the twisted nematic cell. In LCD operation, remember that the birefringent properties of the liquid crystal rotate the polarization of the light. The light may or may not transmit through the LCD pixel that's sandwiched between two polarizers. So let's now talk about the twisted nematic cell. The liquid crystal molecules are arranged in a helical formation, and it's achieved with the alignment layer orientation. So linearly polarized light that passes through the back polarizer will be rotated by 90 degrees by the helical arrangement of the liquid crystal molecules. If the front polarizer is placed perpendicular to the back polarizer, all the light passes through the front polarizer and the liquid crystal display looks white. This is called the normally white mode. If two polarizers are parallel, the pixels are unbiased, and the unbiased pixels will look black, and this is referred to as the normally black mode. So now let's get quantitative and think about a plane wave that enters a liquid crystal cell, and it's got a wave vector k, and it's entering the liquid crystal from the plus z direction, so it's entering this way. The x-axis is defined by the orientation of the directors of the molecules at the entrance, and the polarization of the incident light is alpha with respect to the x-axis. So in order to analyze this, we can turn to Jones vector and basically keep track of the polarization as we propagate through the cell. The approach is going to be to divide the cell into a number of slices and then look at each slice and cascade them. So let's write down the Jones vector for the incident light. J1 is equal to nothing more than Jx, Jy, and this is equal to R of minus alpha, and then here, E of sigma 0, 0. The rotation matrix represents the counterclockwise rotation by alpha. So in the unbiased twisted nematic cell, the directors of all the molecules will be parallel to the xy plane, and they'll form a helix along two axes. We can define a number of quantities that will help our discussion. The first is the linear twist. The linear twist can be represented as psi, and this is equal to alpha times z, and this is alpha naught here. We can also define a pitch, p equals 2 pi over alpha 0. So as I said, the approach here is really to divide the cell into many thin slices that are parallel to the xy plane. All the molecules are parallel within each slice, and each slice is rotated from the previous slice by alpha. So we can define an angle epsilon that corresponds to a thickness d epsilon. D epsilon over epsilon equals p over 2 pi. Or if we want, we can write that d epsilon equals epsilon p over 2 pi. We can define a twist angle beta. So beta equals nothing more than 2 pi d over p. And the number of slices for a cell, S, is given by d over d epsilon. Or if we want, we can write this as 2 pi d over p times epsilon. After the first slice, okay, so here is the incident polarization, we can calculate what we expect the Jones vector to look like. It will look as follows. So essentially, it will be nothing more than O1 equals here, J1x, J1y, and then this is equal to exponential of minus j kx d epsilon, and then here this is going to be 0 and 0, and here exponential of minus j k y d epsilon. And then this is multiplied by the original jx jy. So that's what happens after one slice. If we want, we can write this a different way. Since the molecules in the first slice are aligned with the x-axis, x and y are axes that exhibit two different refractive indices, which we can indicate as follows: n plus delta n over 2, and then n minus delta n over 2. So now we can write that O1 is equal to exponential of minus j 2 pi n d epsilon over lambda, and then here this is going to be the exponential of minus j pi delta n d epsilon over lambda, and then here we have 0, and we have another 0, and this is exponential of j pi delta n d epsilon over lambda, and then this is multiplied by the original Jones vector jx jy. So if we want, we can write O1 in more general terms. We can write this as T of epsilon times J1, where J1 is the original Jones vector. If we think about the next slice, we now need to rotate our coordinate axis by this angle phi, so that the polarization vector is in the coordinate system whose axes align with the optic axes of the slice. So we can define our rotation matrix R of epsilon as equal to nothing more than cosine of epsilon sine epsilon minus sine epsilon cosine of epsilon. And so we can apply the same T of E to find the polarization vector on the exit for the second slice. And so we can repeat the process for all the slices in the cell to obtain the full polarization vector. And the full polarization vector we can write as O, S. And so this is for the limit, really, as S goes to infinity, of O S sigma and then O S tau. And this is equal to nothing more than T of epsilon times R of epsilon. So that's just the rotation matrix. And then to the S minus 1, then T of epsilon, R of minus alpha. And then here, this is going to be multiplied by E sigma 0 and then 0. So essentially, that's what's going on. That's the expression. So really, in order to figure out how the polarization is rotated by a twisted pneumatic cell, we split it up into a series of slices, and then we just keep track of the polarization rotation using Jones matrix calculus. So it's actually pretty straightforward. It's a bit of a mess, but it can be done quite nicely.